Hi everyone. I hope you are doing good. So, welcome to the exam for review session, and this will be our last exam review session for this course. And today I will be discussing on few problems. I think we have about 6 or 7 problems, and we'll be discussing how to deal with problems like this. If you see a problem like this in your exams, so without delaying, let's start. So can you hear me? Can anyone give thumbs up in the chat or something?
Yes.
Okay. Okay, great. Thank you. So let's start with the laws of thermodynamics. So these are the laws that you need to learn for your exams, but the laws of thermodynamics aren't limited to only these three. There are other laws like the there is third law of thermodynamics as well, but that's out of the scope for this course. So at first you need to know the zeroth law. So if you have three systems, outside three closed system, and if you connect them in such a way that if A is in thermal equilibrium with B, so thermal equilibrium means that the temperature of A will be equal to the temperature of B. And if A is also in thermal equilibrium with C, and if B and C are not connected, but even if they are not connected, they will have equal temperature. So it looks like like here you can see that there is like dotted line. That means they are not physically connected. So they cannot have direct exchange of heat. But since they are connected with A, both of them are connected with A, and since they are thermal equilibrium with A, they'll somehow have equal temperature, and thus they will also be in thermal equilibrium. So that's the zeroth law of the thermodynamics. And another important law of the thermodynamics is first law. So first law states that the change in the internal energy of a closed system. So if you have a not closed system, so if you have a system and the change in the internal energy of that system is the work done plus the net heat in that system. So the direction of the work done and the heat is determined, as you can see from this picture. So if you have work done on the system, then your work done is positive. If you have work done by the system, then your work done is negative. Similarly, if you have the heat incoming to the system, or if the heat is entering the system, in that case you have positive heat, and if you have heat leaving the system, then you have a negative heat. So overall, the first law of thermodynamics gives you the net energy in the system that is represented by the delta E thermal, that is work done plus heat. So another important law of the thermodynamics is second law. So second law states that the change in entropy. So entropy is the measure of randomness in a system. So the change in entropy is greater than or equal to zero. So the entropy of a system always increases, or the change could be zero, but it cannot be negative. So I don't think there will be problems related to this law. I'm just putting it here so that you can have some information. Okay, so if you know first law and zeroth law, I think you'll be able to answer these problems. So let's start with question one. So when the sun's light hits the earth, the temperature rises. What happens to the entropy? So as I've already told you that the entropy is the uh, degree of randomness. And when you hit something, so, so if you boil water, so what happens is that the water molecules in that pot, they start to move faster because they gain energy and there is more collision between these molecules, and thus there is more randomness associated with the system. So in that case, your entropy increases. So the answer is the entropy increases. and the entropy cannot decrease because if there is decrease in the entropy, then that means that the system is violating second law of thermodynamics, and thus the such system cannot exist. And there could be case where there is no change in entropy, but in this particular case, when the sunlight is hitting the earth, so that means that there is like a layer of atmosphere, right, in the uh, uh, outside covering the outside surface of the earth. So the molecules in the atmosphere, the gaseous molecule, they start vibrating faster when the temperature rises, and thus the overall entropy increases because there is more randomness associated with the system. So whenever you are heating a system, that means you are increasing the entropy. So if you're riding a car, or if you are driving a bus, in that case, the thermal heat that the engine is giving to the surrounding is helping to increase the entropy of the surrounding. So overall, the system plus the surrounding, the entropy increases. So let's go to problem 2. Which one of the following is true and why? So it is impossible to transfer heat from a cooler to hotter body. So it's impossible to transfer the heat from a cooler to a hotter body. So it's not a true statement because it is possible to transfer heat from cooler to hotter body. So you have read about refrigerators and stuff like that. So uh, usually what happens is that the environment or the room has higher temperature compared to your temperature inside the refrigerator. But if you do work to bring that heat from that colder environment to the hotter environment outside, then it is in fact possible to transfer heat from cooler to hotter body. So example is refrigerator. So it is possible. So that means this statement is wrong. It is possible for heat to flow spontaneously from hot to cold one or from cold one to hot one, depending on whether or not the process is reversible or irreversible. So this statement isn't entirely true. It is in fact possible for spontaneously heat to get lost from hot body to cold one, but the reverse isn't possible. Spontaneous means it can happen without any assistance, but you the heat from cold object to hot one um, cannot be transferred without doing some work in there. So this statement is false, and irrespective of the system being reversible or irreversible, this second statement is false. So that means the correct answer is all of these statements are false. So the only statement that is true is that heat can spontaneously flow from hot to cold one. So if there was a statement like that, then in that case that would have been a correct statement. So is there any question? Okay. So let's solve problem number 3. So you have a 500 joule of work are done on a system in a process that decreases the system's thermal energy by 200 joule. How much heat energy is transferred to her? Uh-huh. Is there any question? Okay. So let me turn on my OneNote. In that problem, you said that uh, you have the delta E thermal. The delta E thermal is negative 200 joule, and your work done is 500 joule, and you need to find the Q. what is your Q? So if you use the first law of thermodynamics, so from first law of thermodynamics, you can say that your W thermal is work done plus heat transfer. So that means your Q is W thermal minus work done, and that is negative 200 joule minus 500 joule. So that means in total you are losing 700 joules. So the heat is going out of the system. So if this is your system, then heat is going out. So your delta Q is less than 0. So let's go to the next problem. So I don't think this one was particularly hard one. If you have any question, you can interrupt me anytime. So before doing next problem, let me introduce heat engines. So heat engines are the systems that can do some useful work if there is some difference in the temperature between the hot reservoir and the cold reservoir. So if you have a hot reservoir, like you can see here, and if you have a cold reservoir, and they must have some temperature difference, or they must have some difference in the amount of heat they have stored in them, then they can do some useful work. That is represented by this W in. And there are also other reverse heat engines that are called refrigerators or heat pumps. So what they do is they can actually transfer the heat from colder reservoir to the hot reservoir. So in fact, this is the heat engine. This one is for the heat engine, and this direction, or this engine is the uh, refrigerator, because you're transferring the heat from cold reservoir to the hot reservoir. So this is for refrigerator, and this one is for heat engine. So the total heat, or the heat stored in the hot reservoir, represented by QH, is the work done plus the heat that is thrown to the cold reservoir. And this is true because energy has to be conserved, and we can see that the initial energy QH is shared between the work done and the cold reservoir. So there is in fact energy conservation here, and the efficiency is given by output work done over the input work done, that is the heat stored in the hot reservoir. And in terms of temperature, it looks something like this. And for a refrigerator, you have quite opposite kind of the formula. So you have QS, that is the heat stored in the hot reservoir, and that is the work done. So in this case, work is done in the system, right? And in the heat engine, work is done by the system. So work done is quite different. So that you need to take care of the direction. And there is QC, the cold reservoirs heat. So like similar to efficiency, the refrigerators also have some terms which determine how much efficient the refrigerator is. So it is usually represented by coefficient of refrigeration, uh, and that is this. So QC over the work input. So the formula is somehow reversed, but not exactly reversed, because here the denominator is the heat of the hot reservoir. However, here the numerator is the heat of the cold reservoir. So in terms of temperature, the coefficient of performance, or the coefficient of refrigeration, looks something like this. Okay. So let's solve this problem. So these are one of the important problems. I think you'll be asked problems like this in your exams, in your final exam. So make sure to practice a few more questions like this. So the first problem is an engine does 10 joule of work. So it's a heat engine. So it does uh, work. The work done by the engine is 10 joules and exhausts 15 joule of waste heat. So waste heat is the QC. That is the heat that is thrown to the cold reservoir. What is the engine's thermal efficiency? And if the cold reservoir temperature is 20 degrees, so if the temperature of the cold reservoir is 20 degrees, what is the minimum possible temperature in degree of hot reservoir? So how to solve this problem? So to solve this problem, what we can do is first, we can draw a heat engine. So you have a hot reservoir. This is your engine, and this is your cold reservoir. Okay, so the heat stored here is QH, and this here is QC. This this engine, this engine does work, and work done is always the difference in QH minus QC. So I think in this case, you are given the work done. Your work done is 10 joule, and your QC is 15 joule, and you don't know what is QH. So for part A, you need to find what is QH. So how do you find QH? You just, if you look at this equation that is here, if you know the work done and if you know the QC, you can find QH. So since your work done is QH minus QC, that implies your QH is work done plus QC. So that is 10 joules plus your 15 joule, that is 25 joule. So now that you have found QS, you can find the efficiency, because the second part asks you to find the efficiency at first. So the efficiency is the work done. For heat engine is the work done over QH. And your work done is, in this case, it's 10 joules. And your QH is 25 joules. So this is about 0.4. So in terms of percentage, so if you want to write it in percentage, it's about 40%. Okay, so that's your efficiency of this heat engine. And the next part, what you are asking is that you are given the temperature. So you are also given the temperature of the cold reservoir. So temperature of the cold reservoir, you are given about 20 degrees centigrade or Celsius. So that is, if you change it into Kelvin. So don't forget to change it into Kelvin. It's very important for heat engine problems. You need to convert them into Kelvins. So temperature in Kelvin is temperature in degrees centigrade plus 273. So this is how you convert it. Okay. So that is 293 Kelvin is the temperature of your cold reservoir. Now you need to find the temperature.
Fuck this!
Sorry? Okay. So let's find the temperature of the hot reservoir. So to find the temperature of the hot reservoir, what we can do is that we have the efficiency already. So well, if you remember the equation for the efficiency in terms of temperature, that is 1 minus Tc over Th, then that this is how it looks like. And if you have Tc, then you can find the Th, because you already know the efficiency from here. Okay, so if you solve for it, then let's bring this term to that side and this efficiency to that side. So what happens is Tc over Th will be 1 minus the efficiency. And since we are solving for Th, let's reverse everything. So, or let's cross multiply. So if I reverse everything, then Th over Tc will be equal to 1 over 1 minus n. Okay? So that means your Th is T sub c over 1 minus beta. So that is your 293 Kelvin 1 minus. So you say use your efficiency in terms of number, not in terms of percentage. So if you have a if you calculated your efficiency to be in percentage, then divide it by 100. So that means your Th is two. It's about, since you are using Kelvin, you will get the answer in Kelvin, so 488.3 Kelvin. And I think the problem asks you to write the Ts in terms of degrees Celsius. So in that case, you need to subtract it with 273 Kelvin. So that is 488.3 Kelvin, 3 minus 273 degrees centigrade. So that's 115.3 degrees centigrade. So that's the temperature for the hot reservoir for this problem.
Excuse me? A quick question.
Uh-huh.
Why did you change it to kelvins if you only had to change it back to Celsius?
If you do it with Celsius, everything, because since you are doing maths here, the factor will be different. So whenever we are talking about temperature scales, or whenever we are solving the problem that depends on temperature, it's better if you I think it's compulsory if you need to work it in Kelvin still, because the SI everything the definition of these equations are defined in such a way that they work for Kelvin scale. So if you, let's suppose if you take here the degree centigrade, here if you take it to be 20 degrees centigrade, okay, and let's calculate the efficiency in terms of degree centigrade. So you found that your Th is 215, right? So if you take 215 here, you won't get 0.4. You won't get 0.4. So that's not possible, right? If your temperature scales were same. So that's why it's always good to do your problems in terms of Kelvin. Only the Kelvins and temperature are same when you are dealing with difference in temperature. The change in temperature in Kelvin unit is always equal to the change in temperature in degree centigrade. But that doesn't mean that your specific temperature T1 at Kelvin will be equal to T1 at degree centigrade. Let me charge me. Did I answer your question?
Yeah, thank you.
I have a quick question about your value that you chose for efficiency.
Mm-hmm.
Why were you able to use the value for efficiency that we got from the workout divided by the Q heat and then put it into the Emax? I thought those were two different values, but you used the efficiency for the Emax. Will those always be interchangeable?
Okay, I missed something. So maximum efficiency of a heat engine. So if you have a heat engine, then the maximum efficiency that this heat engine can have is the efficiency of that heat engine, if it can be somehow converted into Carnot engine. So do you know Carnot engine? Have you been taught in your class about Carnot engine?
No.
So a Carnot engine is a idle engine. So Carnot engine always has 100%, not the 100% efficiency, but the maximum efficiency between any two temperatures. So suppose you have like 20 degrees centigrade and you have 215 degrees centigrade. So at first we have normal heat engine, right? Here we calculate it to be 40%. So, and now since the problem is saying that this is the maximum efficiency of that heat engine, that means this engine has to be a Carnot engine. So in that case, the Carnot engine the efficiency of the Carnot engine can be calculated by this equation. So actually this equation is not for heat engine, not true for all heat engines. This is only true for Carnot engine in ideal cases. So that's why if your problem says that that is your maximum efficiency, the efficiency that you calculated in first part is the maximum efficiency, that means you cannot use this equation. Okay?
Okay, in our problems, will it tell us which kind of engine it is though? Because if it did say that, I missed that, and then also I don't know what that is. So will we be
So-
told that?
So I think most of the problem they will specifically say to you, and they will say it to you if they want you to do the problem using this equation. But I think most of the equations that uh, will be asked in your exam will be related to this equation that involves heat, not the temperatures. Okay, uh, does that make sense?
Yeah.
Um, so let's go to the other problem. So if the efficiency of the Carnot engine, so like here, the problem specifically tells you about the Carnot engine. Okay,
Okay.
so the, yeah, usually it says the Carnot engine, but if it does not say Carnot engine, that means you don't have to worry about the temperature. I think you can just play with heat and find the temperature. Because if they want you to use temperature to find the efficiency, then they must say it has to be a Carnot engine. Okay. So if the efficiency of the Carnot engine were to be 100%, the hot reservoir would have to be 1. So infinitely hot or 100 degrees centigrade, 0 degrees centigrade, or absolute zero. So let's calculate first and the conversion rate. Okay. So let's do this part. This is question 2. First of all, you have a Carnot engine. Okay. This is your hot reservoir, this is your Carnot engine, and a cold reservoir. So that is engine. And, and for Carnot engine, as I've already told you, the equation to find the efficiency is this. So it is in terms of temperature, not in terms of heat. So for this to have maximum, for this to be maximum, that means 100%. This efficiency has to be 1. So, when can this equation be 1? So this can be 1 if this term can be 0, right? If this can be 0, then in that case you can have 1 as efficiency or 100% as efficiency. So when can this ratio be 1? So there are two cases in which this can be 1. One is that either your TC can be 0, so 0 over something is first norm, so this has to be 0. Either TC can be 0 or your TX can be infinity. So if your hot reservoir is infinitely hot, that means something over infinity. So if you have TC over infinity, something over infinity is always 0. So in that case, you can have 1 efficiency. And something over 0. So if you have TC over equals 0, then 0 over TX will also be 0. So in that case, also your efficiency can be 100. Since you are asked about what would be T hot, such that the efficiency of the Carnot engine is 1 or 100% or 100% is the same thing. So in that case, your temperature has to be infinitely large. So that means your answer is that TH has to be infinitely large. Okay, so that is your answer. Okay, So let's go to the next problem. So two ideal Carnot heat engines have same efficiency. They operate between 500 Kelvin and 300 Kelvin. One operates between 500 and 300 and the other between 400 and some low temperature. So what is that low temperature? So usually Carnot engines have 100% efficiency. So that's why they are the idle engines. We don't have Carnot engine that is possible, that is realizable in our daily life. So it's just the theoretical or ideal engine. So we have two ideal Carnot engines. Let's suppose this one is the first one. Okay, one. Let's suppose there is another one. And this is two. So T heart of one is okay. So this has a hot temperature of 500 Kelvin. The cold reservoir temperature TC1 has 300 Kelvin, and this one has T2 has 400 Kelvin. We don't know what is TC2. We need to calculate that. And two Carnot engines, since they have maximum efficiency to be 100%, so they must work between a similar range of temperature. So they differ somehow the efficiency they have to work in such a way that they satisfy the efficiency of one has to be equal to the efficiency of two, and both of these have, in this case, both of them are one because they have 100% efficiency. So let's write the equation for the first efficiency, that is 1 minus T T cold 1 over TH1. Okay, that is equal to, that is into eta 2, that is TC2 over TH2. Okay, so this one and this one get cancelled. And we can also get rid of this negative sign if we multiply with negative 1. So we'll do that in this step. TC2 over TH2. So this and this can be chopped if we multiply with minus 1. So your TC prime is TH prime is equal to TC2 TH2. So as we're solving for TC2, this value, TC2 is T, if I bring that to the other side, I will get TC prime over TH prime times this from TH2. So this will give you the temperature of the cold reservoir. And here as well, I'll remind you that you must use Kelvin scale for your temperature. If your problem had given you the temperature in terms of degrees Celsius, you must change it to Kelvin, because the ratio of two temperature in degrees centigrade or the product of two temperature in degrees centigrade is not equal to the when you convert those numbers into Kelvin and do the same thing. It won't be the same thing. Okay, so if we do this, then what you'll find is you will find 300 over 500 times 400. So everything is in Kelvin. This is also in Kelvin. This and this got cancelled, so it's already get cancelled. And you will get about 240 Kelvin. That's your TC2. So the temperature of the cold reservoir in the second Carnot engine is 240 Kelvin. Okay. So if you have any questions up to this point, you can ask now. Okay. So let me introduce another term that is important for you. So that is the ideal gas equation. So if you have a system that has some pressure, volume, and temperature, and some molecules in it. Let's suppose it has n moles of molecule or atom in it, then the volume, temperature, and pressure follow this kind of equation form, that is PV equals nRT. Here R is the universal gas constant, and the value for the R will be given to you in your exam. And this can also be converted into, so this was the number of moles. The small m is the number of moles. Whereas this equation can also be written as PV equals NKBT, where KB is the Boltzmann constant, and this Boltzmann constant will be given to you. T is the same, whereas your N is not the number of moles in this case. So your N in this case is the number of molecule. So there is a difference between the number of moles and number of molecule. So let me talk about that a little bit. So what's the difference between n, small n, and the large n? So if you have a box, let's suppose, and you have a hydrogen gas or any gas inside it, then if you somehow have 6.023 times 10 to the 23 atoms or molecules, then this equals to 1 mole. So this is at standard temperature pressure. So this number is true only at a standard temperature pressure. So that's how they defined the 1 mole back in the previous century, I guess. And so, but how do you calculate the number of moles if you are only given the type of atom? So if you have a, let's suppose nitrogen atom, then how do you find the number of moles? So number of moles can be found if you know the atomic weight. So if you have nitrogen gas, then I think it has like around 15 as the molecular weight. So it's gram per mole. 15 gram per mole is the atomic weight. So if you look at the periodic table, you can find the atomic weight of nitrogen to be about 15. So if the gas, if it's in the gaseous form, then it will be N2. In that case, you have about 30 gram per mole as the molecular weight. So if you look at here, the number of mole is hidden here, the atomic weight of the molecular weight. So you can actually calculate. If you have like a mass of something given, then in that case you can calculate the number of moles. So if you have, let's suppose your nitrogen number, the mass of the nitrogen atom is given to you, let's suppose. And in that case, what you can do is, let's suppose your mass of nitrogen atom was about 2 grams. Okay, so now you can find the number of moles, because now your number of moles is just Mn, that is the mass given to you, over the molecular weight. That is molecular weight of nitrogen. Molecular weight of nitrogen. And this is true 2 gram over 15 gram over mole. So gram and gram get cancelled, and the number of mole comes to the numerator. So your number of mole is 2 over 15 mole. Okay, and 1 mole contains this many numbers of atoms or molecules, depending on what you are looking at. If you are looking at atoms, then it contains this many numbers of atoms. And if you are dealing with the molecule, then this many number of molecules. Okay. And if you are dealing with N, then in that case your ideal gas equation is PV equals nRT. And if you are now finding N, that is the number of mole times 6.023 times 10 to the 23. Right? If you multiply this number of mole with this number, then you will get M. In that case, your ideal gas equation is PV equals to NKT. But most of the time you only have to deal with this equation. So please keep this equation in mind. And for R, it will be given into your equation set that it will be 8.31 times 2 per Kelvin per mole. Okay, so this will be given to you, and Kv will also be given to you, so you don't have to worry about these constants. So if you have any question, you can ask me. Okay. Okay, so let me discuss another important thing to use. So imagine if you have this similar kind of box that I described earlier, and you have some pressure, you have some volume, some temperature, and somehow the system, somehow you increase the volume of the system. There's a you made a lot, you increase the volume of the system and many powers, so you'll have a P prime volume, and you'll have T prime at your temperature because it's changing the volume. So how do you find the final volume or final pressure or temperature if you know the wish of the primes? Uh, you just yeah, yeah, like the other gas equation. So Pp is nRT. Since your number of moles are not changing here, right? You are only increasing the volume or decreasing the volume. The number of the molecules in there are not changing. That means the number of moles of a molecule will also be the same. So this term will be a constant, okay? And this is also a constant. So both of these terms are constant. So that is your PV over T. Let me bring that to the other side. It is constant. That is NR. Okay. And similarly, uh, uh, this is true for this box as well. Where P prime over T prime will be equal to N prime R prime, N prime R, but N prime is equal to N, right? Because we are not adding any molecules. So that means these two can be equated. Then you'll get this equation, PV over T is equal to T prime. And this is another important equation that you need to remember. If you have given the initial pressure, volume, temperature, and the final pressure and volume, you can find temperature, volume depending on what you asked. So that is this equation. If you have initial pressure, volume, temperature, you'll have a final pressure, volume, temperature given by this equation. Okay. So now let's go for another equation that is E thermal. So E thermal, as I've already discussed you in the first law of thermodynamics, E thermal is the net internal energy of the system. So much of the internal energy is contributed by the kinetic energy. So to find the E thermal, what we do is we average the kinetic energy for all the molecules. So that's why we multiply it with all the molecules. That is the number of all molecules. And so that is n times half the RMS. So RMS velocity is the root mean square velocity. And I want you to remember another important formula that I'll be using in the next problem, which you can't find in this slide because I forgot to mention it there. So KRMS is given by 3RT by M. And in this case, M is the molecular weight. M is the molecular weight of that gas. So usually VRMS we deal with gas. And T is the temperature, R is the universal gas constant, which will be given to you. Okay. Any questions till now? Okay. Okay, so let's do this one. So this is the first law of thermodynamics, right? Yeah, it is. This is the delta E thermal. This is delta Q. This is delta W, but you don't have to remember it. It's in different form, but it is the first law of thermodynamics. The first law of thermodynamics you can always remember using this equation. You don't need to remember this one. And but what I want to remember is formula for the work done. So work done is the pressure times the change in volume. That is the work done. So you need to remember that. So depending on the different constant parameters. So if you have a volume as constant, pressure as constant, or temperature as constant, or the heat change in heat as a constant, there are several processes. So these are the special processes in the thermodynamics. So if you have a constant volume, that means you have an isochoric process. If you have a constant pressure, you have isobaric. So iso means same, and the bar means pressure, right? Iso means same, thermal means temperature. So your temperature is not changing. In that case, you have the isothermal process. And you have adiabatic and isochoric process. So how do we draw PV diagram? So pressure volume diagram for this kind of process. So it's a very important diagram, and I have seen many problems involving this kind of diagrams. Okay, so okay. So how do we draw the PV diagram? So as I told you, the isothermal is delta T 0, your temperature not changing. Isobaric is delta 0. Isochoric is for volume change 0. And lastly, your adiabatic process. Adiabatic process is your delta T, which is not changing in this case. So how do you draw a PV diagram? So if you have two axes, P and V. So you have a volume finite, but the change in volume zero. So if you let's suppose the system had initial volume this one, P1, then as it goes through the time, your volume is not changing. So that means it will be a vertical, right? The volume is not changing. So this is the isochoric process in which your volume is not changing at all. And for isobaric process, your pressure change has to be zero. So imagine if you have a finite pressure, let's suppose here, then your pressure won't change when the system moves forward. Okay, so this is isobaric. The pressure is not changing. There's always this value P1, and this is iso. This is iso. Okay. So now you have to determine how does the isothermal and the adiabatic uh, so how to draw this too. So we are not reading how much more about adiabatic in this part in this course. So for adiabatic, the PV equals to INRT is not valid. In adiabatic process, usually is PP comma INRT, which you don't need to remember because it's not in your syllabus. So the gamma is about 1.4 for diatomic gas, and it is a positive value. So what happens is when you draw the graph for isothermal, the graph will be something like this. It will be curved like this. Okay, so it's the hyperbolic function, and that's because your P for isothermal, the PB, not small, let's think small n, PB and RT, your N and R constant, and if your temperature is constant, here the temperature is constant, so this will also be constant, so your pressure will be inversely proportional to volume. So as you increase the pressure, your volume has to go down. And this kind of nature can be seen out in your graph. However, in adiabatic, since because of this factor, which you don't need to remember for your course, but if you draw the graph, what happens is your adiabatic will be similar to isobaric, but the hyperbolic function will have more slope. Okay, So this is for isothermal, and this will be for adiabatic. So I recommend you just remember that the adiabatic will have more slope compared to the isothermal. Now that's the way to go about it for this course. Okay, so now that we have learned about how to draw the PV diagram, I think we're done with the Euclid's equation. Is there any question? Okay. So let's go to another practice questions. So there are two questions in here. So the first question asks you to find that Mars has an atmosphere composed of almost entirely CO2, carbon dioxide, with an average temperature of -63 degrees centigrade. So it's a very cold environment. What is the VRMS speed of all mole, that means 1 mole of CO2 in Mars atmosphere? So let's solve this problem. So this is Mars, and if this is the atmosphere of Mars made up of CO2 gas, there are molecules in here, and these molecules are not like in waste; they are always in constant motion, so they travel here and there, and that gives it the that's how that's how we find the temperature. The temperature is the average kinetic energy associated with the system. But in case of Mars, the temperature is very low. It's about -62 degrees centigrade. Okay, so you need to first change it into Kelvin. So if we do that, then there's 273 minus 63 Kelvin. Okay, and that is 0, so 210 Kelvin. That's your temperature of the atmosphere of the Mars. Okay, so for VRMS, as I've already told you, the formula will be 3/P/m. So you need to remember this formula. This is the formula, but the formula will be given to you in the equation sheet, and this m is the molecular weight. So for carbon dioxide, your molecular weight will be about 44 gram per mole. Okay. And since you are only dealing with 1 mole in this case, so that is about 44 grams. The problem says your number of mole is just 1 for this problem. So you have 44 grams. You're only dealing with the 44 grams of carbon dioxide. So in kilograms, it's 44 times 10 to the -3 kilograms. Okay. Now I have temperature in Kelvin, your mass is in kilogram, your R is about 8.31, so R will be given to you in the exam 8.31 joule per mole per Kelvin. So now if you find the VRMS, you'll find that VRMS is 3 times R is 8.31 joule per mole per Kelvin times your temperature is 2.10 Kelvin divided by 44 times 10 to the -3 kilogram. And this is about 350 meters per second. So this is very, very high velocity. 350 meters per second is very high velocity. And that's why the atmosphere in the Mars and Moon, they are very thin, because these gaseous molecules in some cases can escape the gravitational field of this planet. That's why they don't have a very thick atmosphere compared to us. Okay.
So is the mass always measured in kilograms, not grams?
You need to use everything in Kelvin if you want your answer to be in. Sorry, you want your everything to be in the SI system if you want your answer to be SI unit. Wait a second. It's always safe to use everything in a SI system. Like that, yeah.
Can I see the graph at the top real quick just so I can take a picture?
This one?
I'm good now. Thank you.
I'll be releasing this node after this end of this presentation. Okay. Now let's go to the another problem. So this one I think is one of the hardest problem for the students, and also I think it is one fast question. It's one of the most important question. Number 2. So what is the QX extracted from the hot reservoir? What is the efficiency for it? So this PV diagram is for a particular heat engine, and the cycle in which this heat engine work is represented by this triangle. And what is the efficiency for the heat engine described by the PV diagram of the figure? So you need to be able to interpret this PV diagram. You need to find the temperature of the hot reservoir, you need to find the temperature of the cold reservoir, and also you need to be able to calculate the work done so that you can find the efficiency. And so how to do that? So you have this graph, okay, triangle, and this cycle. And direction is very important in this case. So the heat is coming out of here. That is minus 82. The coming out of this phase of the engine is 100 joules, and here entering at this phase is QH. Okay, so this is P, this is P. So our heat engine has compression and expansion phases. So here your volume is increasing, so it has to be an expansion phase, and here your volume is constant. So it's an isochoric process, and nothing more is happening in terms of volume in this case. However, there is compression. So our heat engine mainly has compression and expansion phases. So usually the ideal heat engines, the diesel engine or petrol engine or the gasoline engine in the US, they have like this kind of cycle. This kind of cycle. They have like compression, two compression cycle. One is expansion, another is nothing is happening. It's just the isochoric process, and there is again compression. Nothing happens in terms of volume. So these heat engines are the diesel or petrol or gasoline engines. They have this kind of cycles ideally, but this is a different kind of engine. We don't know if it's practically realizable or not, but we're asked the problem. So to find work done from the PV diagram, there's always best to go for the with the across work done is equal to area area of the curve or area of the curve. So by area under the curve, I mean this area. Okay. So the net area represented by this cycle, this area, is your work done. So that's one key thing that you need to remember for your exam. And this one is 200. This unit is centimeter cube. And this one is 600. This is 100. Okay, and this is in kilopascals. So kilo. So do not forget this kilo. So this kilo is 10 to the 3, and to every point in this scale, and that is the number. Okay. So now you are asked to find the efficiency, so you need to find the work done at first. And you also don't know the QX. You might also need that, or you might not. Let's see. So let's find the work done first. The work done is the area under the curve. That is the area of this triangle. And the area of the triangle is half times base times height. So, so, so this is the perpendicular angle. So that means this is the height, and this is your base. Okay. So that is in this case half times your delta base. Base is 1 and 2, so 2 minus 1, and that is change in volume. And delta p times your height in this case is delta p, because this is your height. Okay. And this, so that is your delta p. Okay. So why do you need half? Because it's not a square. If it was a square or a rectangle, there won't be half. Half, there will be just base times height, and that will keep your triangle, rectangle. So half times, what is your change in volume? In this case, you have like 600 minus 200 centimeter cube. So you need to convert that into meter cube. So 1 centimeter cube, or 1 cubic centimeter is 1 centimeter times 1 centimeter times 1 centimeter, right? So in that case, you have 1 over 100 meter times 1 over 100 meters times 1 over 100 meters. And that is your 10 to the negative 6 meter cube. Okay? Times 10 to the negative 6 meter cube. That's your delta V. And the other thing that you need to consider, and you need to look at, is delta V. That is 300 minus 100. That is 300 minus 100. Since you are asked for kilopascals, kilo is 10 to the power 3, pascal is Newton per meter square, that is SI unit, so I'll just write it in terms of pascals. So now everything is in SI. So the answer you'll get in, or the work done will also be in SI, that means it will be in terms of joule. So that is, if you do the maths, then you'll get, it will be about 40 joules, so I'll just write it directly. If you do it, you'll only get 40, and meter cubes times pascal will be joule. That will be your work done. Okay, so you have already found work done that is needed for your efficiency, because your efficiency is work done equal to, that's right. Okay. Okay, now since you have already found the work done, now you need to find QH. So how do you find QH from the graph? So you have 180 joules and 100 joules leaving out of the system, and you have QH entering the system. So if you imagine this should be a heat engine, this is your hot reservoir, and this is your engine. Overall, the two heat are coming to this direction, and this is your cold reservoir. Okay. So that is, if you add up these two hits, this is your engine. If you add these two hits, 180 joules and 100 joules, then that will make the QC, because this is the heat coming out into your environment or to your cold reservoir. So your QC is just 180 plus 100 joules. So your QC is 100 joule plus 180 joule, because these two are being lost by the engine to the environment, and that is our environment is the cold reservoir, the heat engines, and 200 plus 280 joules. Now you have found QC. What is QH? So QH is just sum of work done plus QC. That is 40 joules plus 280 joules. And I think that will be 320 joules, right? And if you find the efficiency, your efficiency will be work done over QH times 100%. So that is 40 joule over 320 joule times 100%. So that will be over 8. So it will be over 100 over 8%. So do the calculation and that will be your efficiency. Okay. You can do it 50 over 4, 25 over 2. I think it will be about 12. Okay. Do you have any question on this one? This one was a tricky one. Now then, let's go to the next set of problems. So before starting the next set of problem, let me talk about thermal expansion. So can anybody tell me, have you studied thermal expansion in your course or not?
Yeah, we did a little bit.
So that means you did study?
Going over it probably wouldn't hurt, but I don't know how everyone else feels about it.
Has Professor Fabi talked about thermal expansion? Has he done any practice problem with you regarding change in length or area with temperature?
Is this video gonna be posted?
Yeah.
I think the only expansion problem we went over was the length one, but I could be wrong. There was one on a homework.
Okay. So yeah, let's go over the. So I think I've listed only the length problem. I think. Oh, so I also listed one volumetric problem. But if you have gone through length problem, then you can easily do the volume problem as well. So let me talk about it. So there are three kinds of thermal expansion. One is the expansion in length, the other one is the expansion in area, and the other one is the expansion in volume. And all of these changes are given by these equations. So what can happen is that when you have already studied the Young's modulus. So in the Young's modulus, you study strain, that is change in length over the original length. So sometimes in higher physics problem, the professor asks you about if you change the temperature of a rod or something like that, then what is the Young's modulus? So problem could be like this as well. But since this is not the comprehensive exam, I don't think that there will be problems related to Young's modulus for you, but there will be problems related to the change in length or the percentage change in length or percentage change in volume if you have dealt with this in the classroom. So these are the equations. So here the change in length when the temperature of longitudinal object is increased by delta T is given by this equation. Here alpha is the coefficient of the thermal expansion. So it's the coefficient of longitudinal thermal expansion. By what factor your length should change is given by this constant. And Li is your initial length. Suppose if you have this as your initial length after increasing the temperature to Tf, your final length will be Lf. And the change in length will be delta L. Okay. So if you had an area, if you had a small area of a metal, let's suppose, and you had an area AI with temperature Ti, and you heated that area, there will be equal increase in length and the width of this small sheet of metal, and it will become a large sheet of metal presented by this large box. And the change in the area is given by gamma. Gamma is also the coefficient of thermal expansion for area, and the gamma will be 2 times the alpha. So that's the important thing, 2 times the alpha. And AI is the area, initial area, and delta T is the temperature change. Similarly, however, for volume expansion, you have beta as your coefficient of thermal expansion for volume, that is 3 times alpha or 3.5 times gamma. So you need to remember how much, by what factor these coefficients are greater than the longitudinal coefficient of thermal expansion. And this could be a very important problem for MCQs. They can ask you what is the ratio between beta and gamma, what is the ratio between gamma and alpha. So keep those values in mind. And that is your beta is the thermal percent of thermal expansion volume. This is install volume, and that is the change in temperature. So if you had a small cube of Ti volume and if it was a Ti temperature, if you somehow increase the temperature to Tf, then your final volume will look something like this. Okay. So let's go to our first problem. The length of a steel beam increases by 0.73 millimeter when its temperature is raised from 20 degree to 35 degrees centigrade. What is the length of the beam at? So that means what is your initial length, right? Your change in length is given to you. Your alpha for steel is given, and now you need to find what is the length of that beam inside at 30 degrees centigrade. The other problem talks about the temperature of the aluminum disc is increased by 120 degrees centigrade. So increased, that means you have a delta T given. Your delta T is 120 degrees. By what percentage does the volume increase? You need to calculate percentage of the volume increase. That is the change in volume over the installed volume. And your beta is given. So let's solve this problem first. So now we'll be getting the thermal expansion. So for first problem, we are given delta L at 0.73 millimeters. So if you had an install length line, your final length was 1.5 millimeter. This delta L with 0.73 that is given to you, and your alpha for steel is given to you. That is right over times 10 to the negative 6 Kelvin. That's the unit for the percent. And your delta T in this case will be 35 degrees centigrade minus 23 degrees centigrade. That is 100 degrees centigrade, and this will be equal to 30 Kelvin. Remember, I told you that delta T will be equal for either you do it for Kelvin or you do it for degrees centigrade. The change will be always the same. But that doesn't mean that the when you do T2 minus T1 for this case and T2 minus T1 for this case, this T2 and T2 they are not equal. They differ by the factor of 273. Remember? So when you are dealing with change in temperature, you can't say that the change in temperature in Kelvin scale is equal to the change in temperature in degree centigrade scale. And I can also say if I change it into Kelvin, that is 273 plus 35, and if I change it into Kelvin, that will be 273 plus 25, right? Or when I do it in Kelvin. And this 273 and 273 get cancelled because of a negative sign, and it's the same thing. Okay. 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 So since we have delta L, alpha, and delta T, now and we don't know the I's, so we don't need the initial length at 22 degrees centigrade. But we know the equation, that is delta L is alpha steel times initial length times delta temperature. So that is your initial length. This Li is by putting everything into the side except Li. That is delta L over alpha steel times delta T. So delta L is 0.73 times 10 to the negative 3 Kelvin meter, and your alpha is 12 times 10 to the negative 6 per Kelvin, and your delta T is 13 Kelvin. Okay, so if you solve this, you'll get it about 4.73. So that was your initial length. Okay, sometimes you might be given the initial length and you might not be given this initial temperature, then you might also need to find the initial temperature in that case. So there could be different tricks that can be done to this problem, but you always use this equation and you find a way how to deal with this problem. It's not that hard. Okay, so in the next problem we have a disk. Okay, we have a disk like this, and it has been heated. So after you heat it, this will be large, and this will be something like this. Okay. And your change in volume, uh, you need to find the percentage increase in the volume times 100. So you need to find this. That is your percentage increase in volume. Okay. So you know that your delta V is beta times Pi times of delta T. And I think you are keeping delta T here. Delta T is 120 Kelvin, and your beta is 69 times 10 to the negative 6 Kelvin. So if you play with this equation, if you bring beta and delta T to the other side, your delta T over, no, you just need to bring the Pi to the other side. If you just bring Pi to the other side, okay, you bring your Pi to the other side, that is you will only have beta times delta T to this side. So if you do this, you'll I think and if you multiply it with Pi times percentage, the beta has to be 69 times 10 to the negative 6 Kelvin. The delta T is 120, and you multiply it with 100, so I think it will be about 2.83%. Please check the math, and that will be your increase in the volume in terms of percentage. Okay. So this is number 2. Do you have any question? Okay, if not, then let's move on. So heat transfer and heat rate of heat changes. So if you have a liquid substance or mainly if you have this one is only mainly for liquids. So if you have a liquid that is or the solid that is having some temperature increase, then the change in heat in that substance is given by Q. Q is mass of that uh, liquid or the object that is subjected to the heat change. C is the specific heat capacity, and the other heat equation that you need to remember is the during the phase transition. So if you have a bucket of ice and if you convert that, heat that ice and it melts into water, then it is undergoing the phase transition from ice to water. So in that case, you have to use this equation, that is the mass of that ice or water in that bucket times the latent heat of fusion. And the other phase transition is when you go from your water to vapor state. So if you have a bucket of water and if you boil it, then everything gets converted into gas. Then in that case, you have m times LP. So if you have a solid like ice, that converts into liquid. And in that phase transition, you have m times Lf. And if you have a liquid that turns into gas after you heat it, during that phase transition, the heat loss is given by this liquid. And if you have a, so these mainly these methods are useful for convection method of the heat transfer. So there are mainly 3 types of heat transfer. One is conduction, one is convection, and another is radiation. So this one is for convection. For the conduction part of the heat transfer. So if you have a rod and if you hit one end of a rod, then after some time you'll feel that heat to the other side. If you are holding that rod with your bare hand, then you'll feel that heat. And that's because the heat, usually the conductors are good material for heat transfer. And the rate of heat lost by the hotter end is given by this. So your K is the coefficient of thermal conductivity, A is the cross-sectional area of that rod, L is the length of the rod, and delta T is the change in temperature between those two lengths. Okay, and if you are dealing with the radiation, so if you are dealing with the radiation coming out of sun to the earth, then the rate of uh, heat gained by the earth will be E. E is the emissivity. So the emissivity will be given to you, so you don't need to learn about the emissivity. Usually, it is a constant that is defined in terms of how much does this Earth or any object that we are looking at is emissive compared to the black body. So you don't need to remember what is emissivity, but it's a constant that will be given to you, and usually its value is very less. And this sigma is the Stephan's constant, which will also be given to you. That is 5.67 times 10 to the negative 8 uh, joule per second per Kelvin to the power 4 parameter square. That's the unit for Stephan constant, and area. Your area is the cross-sectional area, okay, and your T is the uh, actually this has to be uh, powered by 4, factor of 4. So if we are calculating heat change, then you have to subtract two temperatures. So in this case, it won't be delta T to the 4. It will be T2 over 4 minus T1 over 4, T1 to the 4. So I'll show you how to do problems related to these equations as well, although I haven't uh, pasted any questions in this slide. I'll go to one problem each for this equation by the end of this program. So let's at first solve how to do the calorimetric problem. So if you have a hot object and if you pour or if you dissolve that hot object into a cold object like water or something, then what will be the final temperature of the mixture? So these are a very important problem for your exam. So let's discuss how to solve this one problem. Okay, so you have a 30 gram of copper pellets and that are removed from 300 degrees centigrade oven, so they are not very hot, and they were immediately dropped into 100 milliliters of water that was just at 20 degrees in an insulated cup. So insulated cup, that means your heat cannot be lost by that system into the environment. What will be the new temperature? What will the new temperature be? So what will be the final temperature after you mix these two? One is hot and the other is cold. Okay. So the specifically the conductivity of the copper, the spelling of the copper is shown here. Copper is 385 joules per kg total. So let's solve this problem first. So imagine this was your bucket with water. So it was at 20 degrees centigrade. Okay. And this is your copper pellets that you put in here. And I think they were at 300 degrees centigrade. And the mass of the copper was 30 grams. That is 30 times 10 to the negative 3 kilograms. And your mass of water. So mass of water was 100 milliliters. Okay. So 1 ml is 1 centimeter cube. So you can write it as 100 centimeter cube. That is 100 times 10 to the negative 6 meter cube. Right? So this is the volume. Now this is not the mass. Mass can be so. So this is the volume for water. So how do you calculate mass? If you have density known to you, that is density is mass over the volume. And mass is density times volume. So density of water is 1,000 kilograms per meter cube, and your volume is given here. That is 100 times 10 to the negative 6 meter cube. Okay. So this will be about 0.1 kilogram. So that is your mass of water. Now that you have mass of water, you know the temperature of the water. Okay, and let the final temperature uh, after you mix the copper with the water, let the final temperature be T final. Okay, then how do you find the final temperature? So usually, I think Professor Fabi has told you to do a problem like your del Q it will be 0, so your del Q1 for water plus changing heat in copper has to be 0. So uh, yeah, we can also do it in a similar fashion. So what is your change in heating the water? Okay, because the energy has to be conserved. That's why the net heat content uh, when added has to be 0. So heat energy is stored in the copper, and the heat energy is stored in the water. They can't be lost into the environment where everything has to be conserved because this is the insulated, it's the isolated system. It's given to you. So the delta Q for water is given by m water specific capacity of the water plus times delta T water, so change in temperature of the water. And for copper is mass copper, which is specific capacity of copper, okay, times delta T copper. That is so. So mass of water times specific capacity of water. So what is temperature change? So delta T is final temperature minus the inside temperature. So that is final temperature is Tf minus what is the initial temperature of water? That is 0.0 degrees centigrade. And this is delta T, right? And it doesn't matter whether you take Kelvin or degree centigrade when you are dealing with delta T. Okay, so for delta T, you can convert it into Kelvin and calculate delta T. You'll get the same thing. So in that case, uh, okay, let's TF minus 1. And for MCU, CCU, for delta T, for copper, that is your final temperature TF minus 300. So, okay, these are, okay. We are solving for TF. So, first I recommend the students to do the algebra and only plug in the values. That way it is easier. So, if I put TF minus 28 on one side, then that would be your MCU, CCU, TF minus 300. If I bring that from to the other side, now, so we are solving for TF. So TF minus 20 will be, if I divide both sides by MW and CW, that will be MCU, CCU divided by MW, CW, TF minus 300. Right? So now you can plug in the value, and if you plug in the value, the mass of the copper is 30 times 10 to the negative 3 gram, and your specific capacity for the copper is also given, and I think that is 85 joule per kg Kelvin. Okay, that is divided by the mass of the water, that is 0.1 kilograms, which is 0.1 kilogram. Times your specific capacity for water is 4190. So usually it will be given to you in the exam. Joule per Kelvin. And TF minus 300. So So this one is constant. You have TF from here as well. So if you do the algebra from here, you'll I won't be there doing it in details, but I think you'll get it T minus 28 degrees centigrade. So here, and it has to make sense, right? Your mix, your water was at 20 degrees centigrade, your oven was at 300 degrees centigrade, and the temperature has to be between these two temperatures because the copper is losing some heat and the water is gaining some heat. So the current temperature has to be between these two temperatures. And yeah, the temperature of water just increased by 8 degrees. And that's because the volume of the water is very large compared to the volume of the copper that you add. That's why there is only small change in temperature in the water by about 8 degrees centigrade. Okay, if you are getting your answer like somewhat like 10 degrees centigrade or somewhat like 310 degrees centigrade, that means definitely have made some mistake in your calculations, so you need to recheck them. Okay. Is there any question?
Yeah, why did we not have to convert to Kelvin during the problem?
So to be safe, I still recommend you to convert everything into Kelvin. But whenever you are dealing with delta T, the change in temperature, your delta T in degrees centigrade will always be equal to delta T in Kelvin. So if you have done it using the Kelvin, right, you'll get your answer in terms of Kelvin. So uh, here as well, you'll get everything. You'll get your answer TF initially. The value that you get from here will be in Kelvin. It won't be directly at a degree centigrade. And after you convert it, it will be at a degree centigrade. So to be safe, always convert it into Kelvin. Okay. I didn't do it here, but to be safe and to get rid of the confusion, always convert it into Kelvin, and there won't be any mistake. That's the
Okay.
good thing.
I had another question, sorry.
Okay.
I'm kind of confused where you got the molecular weight for the water. I saw you bring in the 1,000
Oh, no,
kilograms.
no, it's not the molecular weight, it's the mass of water.
Okay, and then you got that 1,000 kilograms per
It's
meter.
the density of water.
Okay,
It will
that
be
was
given
my
to you.
question.
Yeah.
Okay, thank you.
Is there any question? Any other?
In terms of the algebra for this question, how do you best isolate TF at the end of the problem?
So for this one, yeah, I can show you how to do this. So you have a TF minus 20, right? So now what you need to do is you need to calculate. So let's suppose this value is your x. Let me suppose this to be x. Okay, this will be some number, and that will be your TF minus 300. Okay, so if you now multiply with x TF minus and minus 1 positive here, that is 300 times x, right? This will be your TF minus 3. So you need to bring the right terms at one side. So let's bring this to the left hand side and this to the right hand side. Okay, so you'll get TF plus x TF. That's equal to your 20 have minus in front, so it will be positive 20, and this will be as it is 200 times x. Okay. Okay. So now if you take TF as common, then you will have 1 plus x, right? If you multiply TF with this one, you will get this answer. Now you have 20 plus 300 times x. So this x, remember that this x is just this whole, I took this whole area to be x. So if you do the calculator, if you calculate, you'll just be getting some number here. So this is adding up some number plus TF that will be maybe 2.3 TF or something like that. So this is just a number, these are just numbers, these are numbers. So you get times and so on. Does that make sense?
Yeah, thank you.
Okay. Okay, let's repeat. Okay. Okay. So let's go to the other problem. So the other one is quite complicated than this one. So in this case, you have a 300 milliliter cup of coffee that is too hot to drink when served at 9 degrees. So for that, we added some ice. That is about minus 20 degrees centigrade, and that was taken out of the freezer. This was at minus 20 degrees centigrade. It will cool your coffee to up to 60 degrees centigrade. So your final temperature is given in this case. So last time we calculated this final temperature, but here the final temperature is already given. So now you need to calculate the mass of the ice that was added. Last time the mass was given, the mass of the copper was given, and it was 130 grams, right? But this time we need to find the mass of the ice. But this problem is more complicated than the last one because your ice here gets melted into water, right? Uh, when it's dropping into the coffee because the coffee is very hot and the temperature is enough to melt the ice. So there is a phase transition associated here. And whenever you have phase transition associated, you need to use this kind of, you need to further use this kinds of basically latent heat diffusion and evaporation depending on if it's nothing or if it's vaporizing. Okay. So let's solve this problem. Okay, so you have a cup of, so this is your cup of coffee, and the coffee was 300 milliliters and was at 90 degrees centigrade when you said it. And you added some ice cubes, and it was at minus 20 degrees centigrade, okay? And the final temperature after the ice was added to your cup, and it gets melted and becomes water. And final mixer, so your final mixture, so half temperature, about 60 degrees centigrade. Okay, so this is your the final, this is your TI, temperature of the ice, this is your temperature of coffee TC, and this is the volume of the coffee green tea. Okay. Okay. At first, let's figure out how to solve this problem. So let's make an algorithm or something like that. So you have ice. That's at minus 20%, and you need to find the mass of this ice used. Okay. So we're done with the mass of the ice. So what happens when you add the ice to the hot cup of coffee? So if you only look at the ice first goes to the ice at 0 degrees centigrade. Then after that there will be a phase transition. So I will represent the phase transition with this double arrow. Okay, and this ice will become water at 0 degrees centigrade. So this is phase transition. Okay. And then this water, that is just the melted ice, the ice melted into water. Okay, so the mass will be the same. This water will now be converted into water at 60 degrees centigrade temperature. So I'm only looking at the ice and the when ice is converted into water. I'm not looking at the coffee. Let's forget that there was coffee. I'm simplifying the problem. So that's one half of our problem. The another half of the problem is looking at the coffee. Okay, I'm separating your coffee and the ice and mixture. So you have a coffee at 9 degrees centigrade. When you add ice, what happens is after some time it will still remain coffee. There won't be any phase transition, but the temperature changes from 90 to 60 degrees centigrade coffee. The coffee is not going under any phase transition, however, your ice is going through a phase transition. Okay. So in each of these arrows, that means in each of these steps, you have the heat loss for heat gained by the ice, and there's heat lost by the coffee. So you need to calculate that first. So here you'll have your heat loss. Let's suppose that to be Q1. Okay. Let's suppose that to be Q2, and let's suppose that to be Q3. And for this, let's suppose this to be Q4. Okay. So all of these are heat gain, and this one is heat loss. Okay. So how do you find Q1? So here, the Q1 will be mass of ice because you are dealing with the ice, and you don't know the mass of ice. You are calculating you are solving for the mass of ice, so you don't know what is the mass of ice. Okay, the mass of ice times C of Ci, that is the specific capacity of the ice, and the specific capacity of the ice is different from water. And delta T, so temperature difference between these two lines, 22 0 degrees. So let me suppose that will be delta T1. Okay. So for Q2, you are having a phase transition from ice to water. So that means we're gaining, so it has to be positive. And I, that is mass of I, times the latitude of fusion, right? And for this Q3, now your water that was formed by this melted ice cube goes from 0 to 60. So that is your Mi. So I could have used MW, but your MW will be equal to Mi because the mass of the ice won't change whether it's melted or not, right? It will be the same. The mass remains constant. So I'll just write Mi here. But CW this time because it's water. This phase is water, it's not ice anymore. And your delta T will be delta T3. Let me write that. Okay, that is the temperature difference between 60 and 0 centigrade. That's for the ice. This is for the ice. Ice converted into water. Okay? That's one part of the problem. And the other part, so this is heat gained by the ice. And this heat gained, this heat was gained from the heat lost by the coffee, right? So let's calculate the coffee from 90 degrees centigrade to 60 degrees centigrade. So you have Q4. So in this case, you are losing your heat. Okay. So there's coffee times specific capacity of coffee will be equal to the specific capacity of water. So remember that. If you are not giving, if you have a liquid that is comparable to water, then you can use the specific capacity of water. So for this problem, the specific capacity of coffee will be equal to water, and delta T4, that is 69%. Okay. So delta Q ice, your net change in your ice is Q1 plus Q2 plus Q3, right? And for coffee, delta Q coffee is Q4. And we know that the net heat, delta Q, has to be 0, which implies that your delta Q ice plus your delta Q coffee has to be 0. Okay. So for easy, if you want to make problem further easy, you can individually calculate all these terms and find the nearest algebraic terms and substitute here. For me, it's fine if I do that. If I do it the other way. So for ice, I have MiCi. So delta T1 is this was delta T1, that is your T final minus T initial. So 0 minus 20. There is 2 minus, right? So your delta T1 is 0 degrees centigrade minus 20 degrees centigrade. So this is So you can, to be safe, I recommend you to do everything in Kelvin. It's fine if I use 2%, because you get the same thing. You'll get a factor of 20 when you use Kelvin to be centigrade. So that is this product, Q1, this time Q1. Now let's find Q. Q2 is your MI times RF, so I'll just write it MI times RF now. Your LF will be given, this LF will be given to you. And for Q3, you have your MI, which will be the same, and CW, that's the specific capacity of water, so MI, CW. However, the temperature change is different. It is 60 minus 0, final answer is always 6 degrees Fahrenheit. And 0, that will be 60. Loss. So this one is for the ice. Okay. T3 was 60%. 70% rate, which is only 60. Alright, Kelvin, so you know that Kelvin is 0%. Okay. So let's do it for coffee. So for coffee, you have MC, CW, because we are taking specific capacity of coffee to be equal to a specific capacity of water for this problem. And your delta T is 60 degree minus 90 degrees. So delta T for here is 60 degrees minus 90 degrees. So that's about negative 60 Kelvin. So that will be negative 30, that's Kelvin. Okay. So now the only thing that's unknown to you is MI. Rest of all of the terms are known to you. So MI, your CII. So the for ice, the specific capacity will again will be given to you. So that is 2090. So for kg Kelvin, that's the specific capacity of the ice times 20 plus MI. We don't know MI, we need to find MI. So MI will also be given to you. There's 230,000 joule per kg. And this water, the water is 1190 joule per kg. Kelvin times 60. Okay, this is your question. Plus, what was your mass of the coffee? So the mass of the coffee wasn't given to you. You were given the volume, right? The 300 milliliters volume. And if you look here, the volume will be 300 centimeter cube, because 1 ml is equal to 1 centimeter cube. That is 300 times 10 to the negative 6 meter cube. And since we are taking coffee and water to be similar fluid, we'll take density also to be equal to that of water. Okay, so that volume will have density, then that gives us the mass is density over volume. So mass is density over volume. So density is mass over volume. So the mass is density times volume. So if we do it, you'll have 300 times 10 to the negative 6 plus. So this will be this one. This will be your mass of coffee. Okay. So that is your mass of the coffee is 300 times 10 to the negative 3 kilograms. And we are taking the specific capacity of coffee into that of water, which will per kg Kelvin, and the change in temperature will be minus 30. That's 0. So now you have everything. Now you'll have like xmi plus ymi plus gmi, so xy is here, depends on this multiplication. So now you can add and you'll give a certain number times mi. And if you take, there's a negative sign, so there will be a negative sign, and if you take this whole term to the right hand side and divide with the added term in the left hand side, you'll get mi. And this will be equal to 0.61 gram. You'll get your mass to be 0.06 kilograms, which will be equal to 61 grams. So it's fine, you can leave your mass in terms of kilograms, but just to have a better understanding of the order of magnitude, I will keep them in terms of grams. Okay. Do you have any questions?
I think for this one, I was kind of confused how you sort of determined, you have T1, T2, T3, T4, and there's like 4 different things there. And same with the
Yeah.
Qs. I think I was kind of confused, like how you
Mhm.
knew to, like how to split them up and when you use them when you're kind of putting everything together at the very end.
So when you are dealing with a mixing of two things which are undergoing phase transition, you have to look things independently. So here I'm looking ice and water as two independent things. They are dependent on each other because the heat lost by the coffee is being gained by the heat ice, right? But I'm trying to split the problem so that we can solve it easily. So to do that, you only look at ice at first. So you don't look at coffee at all. So you only look at the ice. So your ice wasn't necessarily at minus 20 degrees centigrade. This ice cube was at minus 20 degrees centigrade. And when it starts getting heat from the coffee, it will at first change into ice at 0 degrees centigrade. There will be a phase transition, and then the ice will change into water at 0 degree, and after that, the water will eventually heated into water at 60 degrees centigrade. So there are, uh, because of our formula are based in such a way that either we know the heat change in phase transition or we know the change in heat when we are heating out within the same phase, we need to break our problems into this kind of structure. So if you had a water and vapor, like vapor-like situation, so suppose if you want further heat it to for further heat at this water, then in that case you will have like water goes to 60 at first, from 60 to 100 degree water, and there will be a phase transition that will be MI times L, and then will be a vapor at 100 degrees centigrade. So it goes on. This series always goes on. But here we were the final temperature was only 60 degrees centigrade, so I stopped here. So for coffee, if you look at only what happened to the coffee there was no phase transition because coffee still remained into the liquid phase, but the temperature decreased from 90 to 60. So regarding the temperature, so for mass, I think it's easier if you only look at the mass of the since we are looking at the ice only, so you are only considering the mass of ice. You don't need to consider the mass of coffee. You are only looking at the ice. So that is my is your mass of ice. The specific capacity has for this case has to be the specific capacity of the ice because you are going from ice form to the ice form. So there is no phase transition here. You are within ice phase transition, and the change in temperature is the temperature difference between two endpoints of that phase. So since you are having phase transition after this point, after 0, you will have a phase transition. You will have a water. That's why you need to take the endpoints. And that is 0 minus 20 degrees centigrade. That is 0 minus 20 degrees because your delta T is always T final minus T initial. So the final temperature was 0 minus the initial temperature was 20 degrees centigrade for this case. So that's why Q1 had therefore T1 had when you are going to change the temperature. Here you are having phase transition, and we don't use this kind of we don't use MC delta for phase transition. For phase transition, we use MI times M times L. So it could be LF equals phase transition from ice to water, and it would be LV equals phase transition from water to vapor. And similarly, after the phase transition, you again reach to a water phase. So there was liquid phase, all right? So we are going from 0 degrees centigrade to 60 degrees centigrade water. There is no phase transition, and that's it. So you only to this one, and now you choose this problem. So you only have we only have these two options. So that's why we break our problem into sets of these two equations. We have this from the uh, same phase from the same phase heating mechanism. Yeah, was that helpful?
Yeah, that was. Thank you. And then the only other thing I had was, how is it that you could then also know that the Q ice plus Q coffee was equal to 0, and then you can set the whole thing equal to 0?
Yeah, it's the heat conservation of energy. So your ice has some heat in the cellular unit. I mean, it has lesser heat, but it has some heat, right? And it gains and your coffee also had some heat. So coffee had more heat compared to the ice inside less heat. But as soon as you drop your ice into the coffee, what happened is that your ice gained heat and your coffee lost heat. But since this is the isolated system, uh, here we are not supposing our heat is lost to the environment. There is no loss of heat to the environment or any of the losses. That means heat lost by coffee has to be equal to the heat gained by us. So this is a conservation of energy. That means your net heat change, or that is your heat gained by ice. So this is the heat gained by ice, has to be equal to the heat lost by coffee. If you look at closely here, del Q ice will be equal to del Q coffee. This is heat gained by ice, that's why it's positive. This is heat lost by coffee, that's why it's negative. So that's why we're dealing with the energy conservation principle. But, yeah, that's it.
Okay, gotcha. Thank you.
Is there any other question? Okay, if not, then let me do two more extra problems, but I will try to do them very quickly, under 5 minutes. So you already asked these problems in your exams. I forgot to mention this problem. So previously I talked to you about delta Q over delta, this formula, right? Delta Q over delta T is Q delta change in temperature over length. So this is for conduction problems. So when you are, suppose if you have a, suppose you have a rod or any metallic steel scale like this. Okay. So there's some metal like this, and if you hit this freezer, then what happens is the molecules from here, they which are vibrating, and this vibration goes to the other end, and this region will also get heated eventually. So how does that happen? That happens due to the conduction. The heat transfer is due to conduction. Okay. So if you have a temperature difference, like if you have like a metal rod and if you have like 250-degree heat initially, and the other ends becomes 5 degrees centigrade due to this conduction. So there is this is the, let's suppose this to be T1, and let's suppose this to be T2. Then your delta T is 250 minus 25. And since the change in temperature will be equal in Kelvin, equal to 20.5 Kelvin. And now you know the delta T, and your area will be given to you. So the area for this problem, let's suppose is to be 200 meters square. And let's suppose the length will also be given to you. Let's suppose the length is about 2 meters. And so how you find the rate? So now this del Q over del T will give you the rate of heat transfer from this hot into this cold end. Okay, this is hot. So the rate of heat transfer due to conduction. And this K is the coefficient of thermal conduction, and this will also be given to you. For this case, I'm supposing it to be 181 watt per Kelvin. So Kelvin meter. So if you solve this problem, now what you will get is delta Q over delta Q will be K is 4.0181 watt per meter Kelvin times your, you can K to be that, your area is 200, right? 200 meters square, and you have 225 as your transient temperature over length. Length will be about, length is given as 2 meters, so 2 meters. So if you do this right, since this is heat, that has in joules, and delta T is time, joules per second. So I expect equation to be in joules per second. That is 200.425. So this will be the value if you do the calculation. And joules per second, energy over time, it's power. That's in watt. You can leave it at joules per second. That won't be wrong. So, so that will be your rate of heat. Conductor. So sometimes what they ask is sometimes you won't be given this term. So you'll be asked what is DC or what is T4, and for that you will be given this value. So sometimes you'll be given this value instead of this, and you'll need to calculate. So you can do that easily if you have some knowledge of things like this. Okay. So that's one kind of problem. So the other kind of problem will be related to radiation. This will be our last problem for today's session. So let's suppose there is a person in a dark room. So let's suppose there's a dark room, there is a person, and this person is on clothes, so he's not wearing any clothes. So and he's losing heat to this room, dark room. So dark room is in has temperature of 22 degrees centigrade, and the person's skin. So the skin has person's skin has temperature about 30 degrees centigrade. And this person is losing the heat, and this loss of heat without any touch or without transfer of any material is known as radiation. So it's the way by which we get heat from the sun, right? So at first, let's suppose our area of the person was given to be 1.5 meters square, and the uh, temperature, let's suppose temperature of person was 30 degrees centigrade, and temperature of the sun was given, not sun, sorry, the temperature of the room was given to be 22 degrees centigrade, okay? And the investigative of the person's skin was given to be 0.17, let's suppose. Then I have already stated to you the formula del Q will be E sigma A times T of the losing. So in this case, it will be T to the power 4 minus T to the environment due to the 4. So in the slide, you will see the formula to be like this. E sigma A T4. But this is not the change. For change, you need to calculate the difference between two. So if you have 1, you have 2, okay, E sigma A T2, then you need to, if you calculate the change, then delta Q, and delta Q will be E sigma A due to the 4 minus 10. Okay, so I'm saying that's why I'm taking this kind of situation. Here we are not dealing with delta to 4. It's not delta to 4. We're doing Tp to the 4 minus Tr to the 4. So we cannot directly subtract these two and raise the power by 4. So that's why we need to convert it into Kelvin. So we need to add 270 plus 30, that is 6. This is Kelvin, and for this 270 plus 20 centigrade, that's 5, 9, 10. Okay, so now if you plug in every value, so it's 0.97 times your sigma will be given to you, it's 5.67 times 10 to the negative 8 watt per 5.54 meters square. That's the unit for sigma. And if you use 5.67 times 10 to the negative 8 here, and if you use area to be 1.5 meters square, that is given to you. And if you use your temperature, 364 to the 4 minus 295 to the 4. So this is the important part. So remember to at first raise the power by 4, calculate the value, and only subtract after that. And in that case, you'll get about negative minus 99 watt. So this negative means that person is losing heat by radiation. Okay, this is how you deal with the problem. So sometimes you'll be given this rate of heat loss again, and you need to calculate the temperature of the environment. Sometimes they might ask you the temperature of the hot body, so you can do the problem. So, do you have any question in this problem?
For this one, if you were given, sorry, go ahead.
Yeah,
you're-
you can. Yeah.
Oh.
I was just gonna say, so for this one, if you were instead given not the temperature of the person and the dark room, but if you were given the temperature of the person, you know, like before and after, would then that be a situation where you would do delta T? Because I think I was confused why you said it wasn't delta T for this one.
In this case, you don't have to deal with the final temperature of the person. So you are only dealing with the temperature of the body that is losing the heat. In this case, it's the person. Sometimes it could be sun. So, right, sun is radiating the energy, and your earth, this part of the earth is getting the energy, and the area will be given to you. Temperature of the earth will be given to you. Temperature of the sun will be given to you. But you won't be given a final temperature of sun or the final temperature of the earth. So we are not dealing with final temperature. We are only dealing with initial temperatures. Okay, so you don't have to take care about the change in temperature. We are not dealing with the same objects change in temperature. We are dealing with different objects. So these two temperatures are different objects. When we were dealing with the temperature change, that is in previous problems, we were dealing with same objects. Sometimes we were dealing with a rod, sometimes we were dealing with a cup of coffee, or we were dealing with change in temperature those in the same system, right? Same object. Here we are dealing with one object losing heat, but we don't need to take care about the final temperature. We just need to insert temperature. If we find the way to reproduce this sun or the hotter object is losing heat. So we don't need to take care of that.
Thank you.
Person.
Yeah.
Is that what the A is standing for in this equation?
Sorry, I can't hear your voice is very quiet.
So because you put that the person is losing heat, I'm assuming that the area, the A value in this equation is the area of the person.
Yeah, it's the area of the skin of the person, because the person is losing heat. Since the person is not wearing any clothes, so he is losing heat from all the part of his skin. So it's the total area of the skin of this person, which will be clearly given to you.
Okay, and could maybe ask like a question about like how much heat is being gained by the room through radiation, and then in that instance we would use the area of the room. Is that correct?
So yeah, maybe I told here in a wrong sense. I think the area has to be the one area has to be the part of the body which is emitting the heat. So in that sense, you don't need to worry about the area of the room. So here, I think you only need to. I think the person will only give you the area of the sun, which is radiating the heat to the earth. So I think that it will be clearly given to you when you're dealing with that.
Okay, that makes sense. Thanks.
Are there any other questions? So if there are none, then that's it for today. I'll post this problems Of course, these problems in Canvas are the lecture notes in the Canvas. So happy studying and happy New Year. It was nice getting these lessons with you. So if you have any other questions before your exam, you can email me and we can set up a Zoom meeting, or you can just ask the questions in the email. I can reply you within 2 hours. So thank you for your time. Good night.
Thanks for your help.
Yeah.
Thank you.